Oops. For fun, okay? Let's try now. Ask easier questions and questions that relate to you. Why do we have ocean tides? Why do we have ocean tides? Because of the moon, right? If that is true, why do we have 2 tides a day instead of 1? Correct or not? If it's only the moon, we should only have high tide at night. Agreed? Why do we have 2? Right? Mind blown, right? If you have not thought of this question before, you'll be like, oh my god, what just happened, right? Anyone? Huh? Sorry? Do you understand? No. You know what I'm asking? Yes. You have a very surprised expression, so I'm not sure. Huh? The moon orbits the earth twice a day. It must be true. Because there's a no, it's not true. Okay, let's look at it. It is true that when the moon is above, let's say Singapore, right, the water around Singapore fills the tide. But the opposite is also true. The water that is at New York, right? Singapore is roughly at the opposite of New York. The water at New York actually does not fill as much pool, right? It's a weak pool. Agree? Look, the force here is actually weaker. So naturally, and because it's spinning, right, it tries to leave the earth. Okay? So don't look at the earth and the water as a fixed picture. Earth is spinning, the water is spinning. It tries to, if you spin something, it tries to stretch out, right? If you take a prata and you spin, it stretches out like a pizza. Pizza, more international. You take a pizza and you spin, it stretches, right? It's because there's not enough force to pull it in. So same thing, right? If you take the water and you spin, it spreads out. Right? Because there's not enough force to pull it in. So when the moon is actually here, there's less force here. That's why it stretches out. Okay? Simple answer. Not because maybe there's a dark moon, right? The dark side. Okay, no. Not Transformers. Okay. Black holes, not talking about it. Moving on. Okay, yay. Fluid mechanics. Yay, simpler stuff. Pressure is force over area. Yay. That's what you learn. But what force, what area? Perpendicular force, perpendicular area. Alright? The normal forces to the area. And Mr. Julius Chan told you, right? Area is a vector. D, is the differential. So the pressure is the differential of force over the area. But most cases, don't worry about that. Very few cases we talk about that. Most of the time we just use this. Yes. Why a triple arrow? Why a triple line? I'm also not too sure. Let me figure this out. I'll tell you. Good question. Okay, Archimedes principle. How many of you have your forces lecture already? Okay. Archimedes principle, upthrust. It's basically upthrust. So when you place an object in the liquid, the pressure acting on the object will be different on all sides. The pressure will be larger as you are lower in the liquid. Using H rho G, the pressure will be larger. Pressure on top is less. The net difference in the pressure and the area gives you an upthrust force. Okay? What is these two pictures? Fluid replaced by the body of the same shape experience the same buoyant force. So on the left, this blue thing is actually the fluid itself. If you imagine this to be a liquid, right, and I have some special power where I can create a tiny membrane around it. It floats right there. If I remove this and I put in a mass of exactly the same shape, that upthrust on this liquid will be equal to the upthrust in the object. Which then allows us to say that the upthrust on the object is the mass of the fluid, or is the weight of the fluid displaced. Because here, this fluid is not going anywhere. It's more or less stagnant. You put water in a pool of water. The water stays where it is, right? Because the density is the same. It does not move. You take a very light plastic bag, you scoop with water, you put inside a pail, it more or less stays there and floats like a jellyfish. If the plastic bag is really, really thin. Right? That just means that the upthrust is equal to the weight of the mass of the bag being thin enough, being small enough. Right? If I replace that volume and become metal, that metal will experience the same upthrust force. Okay, that is a key idea of Archimedes. The moment he realized that. Sinking and floating, I'm not going to bore you. Mr. Chan will teach you that. Quick quiz for fun. Have you all learned upthrust already? Yes, okay, even better. Try this. Look and guess. What will happen to the water level when pure ice melts? Okay, we have an answer. There will be no change to the water level. Very good. Why? Because the mass of the ice when melted will become mass of water. Upthrust is the same volume of water. Right? It melt into the mass of water that is being displaced by the ice. Okay, very good. Air bubble. Why?
In extreme cases, if it's just an air bubble.
Really? Let's see. Is there an answer? Same, almost. Same. Drops. Let's look at the last one. Why does it drop? Okay, or why this one and why almost? Listen up. When you have air in the ice, the water is supporting the weight of the air and the ice. So you displace the mass of water equal to the mass of the water and the air bubble. But the mass of air bubble is almost close to zero, which is why the water level stays almost the same. Liquid water, no difference because it's supporting the weight of liquid water itself. Iron washer will be the one that most clarifies everything. You have ice, when you put it in water, a part of it sticks out, right? Iceberg, right? The iceberg you see in the National Geographic and describe sticks out. If I dig open the ice and I put in a chunk of metal and I close it back, the iceberg should sink. Correct? Iceberg should sink. Now, when the whole ice melts, the washer sinks to the bottom. Right? So initially, this water is supporting the mass of the iron washer and the ice, displacing as much water as it can to support it. But afterwards, it's only supporting the water because the iron washer goes to the bottom, no longer experiences upthrust, but it's not enough to float it. So the upthrust it experiences less than its own mass, which means that now the mass of the water being displaced will be less. Okay? Tough? Okay, never mind. You have it in your tutorial. This is your tutorial question. I have, when I was teaching forces last time, I used this in the tutorial. I'm not sure you all still have it. I think you all have. Skip. If If not, no time. Ideal flow of liquid, steady flow is called laminar flow. We assume incompressible, that means the density stays the same. A non-viscous flow, internal friction is neglected, although there is. Irrotational flow, no angular momentum, there's no spin about it. Okay. Which is all wrong, because there is, all this there is, and can cause violent explosions if you don't consider them. But never mind, let's move on. Assuming all this, in some extreme cases, in most cases, extreme of normal flow, this is not a problem. Okay, these are flow lines. If you open your tap, you can see that the water at the top is large, right? The radius, the cross section is large. As it flows down, it becomes thinner, right? Why is it like that? Because it's always like that, right? But we can explain it here. We can explain it here. Using this equation, the equation of continuity. The question is, why? What does this mean? The liquid does not compress. The volume of water passing through this point over a period of time must be equal to the volume of water passing through this point over a period of time. Do you agree? Right? If not, there will be a build-up of water somewhere, which will be a problem, right? Or there's a leakage. If you assume that to be true, essentially it's just volume 1 over a certain period of time is equal to volume 2 over a period of time, allowing you to get this. Okay? If the densities are the same because of non-compressibility, in university you probably have compressible liquids, then you have a lot of trouble, but now we use the easier one. You have just this A1 V1 equals A2 V2, easy stuff. There you go, right? Find the diameter of the stream 13 cm below the opening of the faucet. 13 cm below, assuming 0 KE, a 0 velocity here, well, close to 0. Here the velocity will obviously be higher because it's lost a certain GPE. Is it? Oh wait, there's a certain flow rate already. Sorry, my bad. Here we have certain diameter, we have this volume, so we have a certain flow rate right at the start. Okay? Rearranging, we can find the velocity to be 10.6 cm per second at the start. My bad, sorry, there is a flow, there's a certain velocity at the start already, 10.6 cm. When it travels down 13 cm, right, the velocity should be higher using conservation of energy. Once you know this, you know how V1 relates to V2, using the equation of continuity. This is easy. Don't shake your head. This is okay. That's okay. Yes. The hard one is the hard one. This is the easy one. Must be understood. This one class understand, No, I'm serious. This one really can do one. Just spend your time at it. Okay, can do one. The previous one, spend a lot more time on it. Okay, and try to do it. Okay. But once you have that, you can put in the values that you see on this, right? Which explains, you see that diameter has decreased. Right, the diameter has decreased. So the first equation I showed you in fluid dynamics is the continuity of flow equation. Last one, last equation. Bernoulli's equation, you hear before? Bernoulli's equation is supposed to teach you about how airplanes fly. If you look at the wing of the airplane, the top part, the air flies faster Below, the air flies slower. The difference in velocity causes a pressure difference, causes an upward force, causing lift. Bernoulli's equation. Okay. We start by deriving it like this. Work done is force times distance minus force times distance 2. It's okay. Change in kinetic energy can be derived. I will send you all the slides, don't worry. Okay? So all this you will see. Your textbook will also have all this, don't worry. Okay? Can see how this is done? It's just half mv squared minus half mv squared. Yeah? This and this is not related. This is by itself, this is by itself. But realize that these two are actually equal, right? Of course, you must also put in GPE, alright? Problematic. You put in also GPE, then you have a lot of pain. So the total, this part, work done, causes a change in KE and a change in GPE. Simplifying, you get this equation, which is what you need to remember. Now, most of the time, the height part is disappeared. It's not there. Most of the time, at your level, Olympic, I'm not so sure, right? Probably not there also, right? Most of the time, the height part is not there. You only have P1 equals to half density V1 square equals to pressure 2 plus half density V2 square. Right? This is an application of this idea. It's the application of this idea. How do you measure the speed of liquid flowing in a tube? You put your head in, right, and you feel the pain. No, right? No, right? There must be a quick way to measure it, right? You put in a pedal. What if it's a very small tube? Right, you do this. If you look at using Bernoulli's equation, we know that if the velocity is higher, the pressure must be lower. 是不是啊? If the velocity is higher, the pressure here must be lower. 对吗? You all know or not? If V2 is high, V1 is low, naturally this one must be lower than this. Yes? If the pressure is high, it will cause a difference in the liquid columns. Okay. So you can find the difference in the height h and find the velocity 1. This.
So there's a pipe near the ball and you put a tube and it filling with water.
You said it's a small tube.
Small tube. You can do this. Yes.
Doesn't it just fall away?
That's a good question. Let me think about this. These ends are they open or closed? Yes? Which one? This one? This one is from here. It's given here. No, you have to memorize it. You have to memorize it. Sorry, a lot of equations, I'm so sorry. Because I have really a lot of things to teach you all. Because the classical part is very large. Later on, the parts behind will be more focused and more directed. Oh. Yes. No, speed is faster, the pressure is lower. Pressure is lower. It's a good question. Your question, if you poke a hole, what will it actually happen? Let me think about it. I think we are talking about a tube. Let's consider a tube like this. The water flows like this within a circular path. It doesn't flow away. Then this question can be resolved. Yeah. It flows in a circular path. This question can be resolved, or it's a continuous flow. Yes, but I agree with what you're saying. But this is the theoretical part. If we do it like this, the water doesn't leak anywhere. You can actually find a difference in the height like this. It's true. But in the normal pipes, probably there's a different way to measure it. Okay. Let me think about it. Alright, last question. I know you're tired, so am I. Okay. Oh my, I wanted to go through the tutorial, but I will send you a tutorial answers. The tutorial actually is quite easy compared to the things I'm presenting here. Okay, last part. You want to see? Okay. Pressure difference across the needle. What's the rate of flow through the needle for blood transfusion? You all been to a hospital, you all know when they stick things in, they always raise the bracket higher, right, than your body. Why? Why do they put lower? They put lower, then your blood flows back out. You must put higher. So if you raise higher, there's a pressure difference, right? This pressure difference will cause a certain flow rate. How do I get this equation here? What's all this equation? Do you all know? Yeah. Let's look at what we have before one more time. How do we get this? This equation just boom comes out from nowhere. How do you get that? You all know? No. Any idea? Okay, let's see what we have. We have the continuity of flow equation. A1 V1 equals to A2 V2. Yes? We have Bernoulli's equation. How do we get this? Actually, I'm also not too sure. Huh? The eta, right? How did they get this? Yeah, where did this come from? The question, let me look at the question. The question also didn't say. Yeah. Okay, I apologize. I should have spent a bit more effort looking at the last question, which I did not. I will record this and I'll put it online. All right. Yeah, I'll record this later.